speaker contributed to a slightly shorter talk by Michael Engel from Erlangen and Quasicrystals and dense packing from the Colloids. So, go for you now.
Thank you very much for having me here and the introduction. And I shortened the title a little bit compared to the program because I also had to shorten the content of the talk to 30 minutes. But you already see on this rather futuristic first slide where we are going. So we have tetrahedra, and we are trying to pack them in space. And one important theme in my talk will be a lot about experiments. So what we'll do here is the theory is actually pretty old. At the beginning of the talk, I will wrap up the theory, which goes back to 2009, 2010. So it's almost 15 years old, but all the experiments are new, and then there are new few aspects also on the theory side. And here you already see the ideas. So we have the tetrahedra, they can pack theoretically. They can also make these clusters, spherical clusters, but they can also form quasicrystals. And here you see sort of this is actually experimental data. You see sort of a diffraction image here from small angle X-ray scattering, and I will show you how we get there. So this image didn't exist on its own. This was part of a journal cover. So we got an artist making this from experimental data. So this is not a real image. This is just computer rendered, but this just appeared last week. So this is super new. And okay, thank you. And yeah, so there are very important are the experimental collaborators who I should give a lot of credit, because without them this work wouldn't exist. And there is the group of Indiana from Xing Yi, a long-term collaborator. They're making these particles. So we'll see these are small gold colloids. So they're really gold. And especially Yi Wang and Yun Chen, who made the structures. We had in FAU, I'm coming from Erlangen, Germany. We have a very good electron microscopy group, and they did tomography. So I will show you some tomography data. There's especially Alexander Goetz, who just finished his PhD, and Benjamin Atteleo Subiri, a group leader. They were in the group of Edmund Spicker. They were very important. And Rui Peng Li, he did some small angle X-ray scattering. He actually made this emissions. Okay, so my group is working on different topics. So we are looking at structure formation in fluids and solids. So that's the theme of my group. We are doing computer simulations, and for the purpose of this talk, we'll look at a specific system of structure formation, which is on nanoparticles. That's a very common theme. I've written a very long review on this topic. So those of you interested to get into this field can read this up. And here I quickly summarize where this is all situated. So we can actually make small polyhedra. So we heard a lot about polyhedra yesterday, and I think there are a few more talks on polyhedra. So we can make real polyhedra on a nanoscale, so 5 to 100 nanometer edge length. We can make them in really large batches, billions of these particles, very monodispersed. And you will see that they're super monodispersed. So I'm always amazed by how monodispersed we can make. They can make different shapes, cubes. Recently also tetrahedra, they can make them branched, and a lot of these shapes. But the problem is you cannot just make the shape, because if you have a small chunk of metal, for example, floating in solution, and there's another small chunk of metal, they would meet, they would just form a bigger chunk of metal. There's nothing that keeps the surface from getting together, except if you functionalize the surface, so you put like a buffer layer on the outside. They're called ligands, so small molecules, organic molecules. This is usually inorganic, this is organic. You put it on the surface. It's like a hair on your head. It's keeping the surfaces apart, and this way they cannot join. But this has also some problems or advantages depending on how you will see it. First of all, when you have these ligands, these molecules, they're interacting with other ligands, so they can be attractive. Another thing is when you put them on the surface, they will round the shape a little bit, because it's like a layer around. So that's something, if you want to study packing of shapes, that can be important to consider. And then you have that all in an environment. So when you really think about making an experiment, that's super important. You have things like maybe you can do an electric field, there's depletion, there's temperature can play a role, confinement, so all of these effects play a role. And eventually you can, so it was a bit fast, you can make real materials out of this. And what I want to point out here is also that There are different length scale and time scales important. So this is a really complicated problem to model thoroughly. But we will try to make it very simple, look at shapes that are effectively hard. And that was also the goal in the experiment for this purpose of this talk. So we look at essentially hard sphere packing. So you see the core is this size, the surface is relatively thin. So to not round the shape too much environment, and also connected to the length scale, there's a time scale. So some things are very fast, the ligands, they move super fast, and some things are slower. So typically an experiment to make such a structure that is at the top here takes from a few minutes to a few hours, usually, rarely to days. So you can actually, I've seen some experiments where it's pretty low tech actually. Like the structures that you get out are super sophisticated, very small scale, but you first essentially it's old scale chemistry. You're pouring together different substances and you're growing these nanocrystals, and then sort of more or less with your hand you can sort of lift this off from the surface of a liquid. So it's you don't need any expensive technology, but you have to know what you're doing still.
Can I say something?
Sure.
Just on the slide back, sorry.
Oh,
geez, I'm
yeah,
sorry. That's just the time, space.
Yeah.
I didn't quite get it all because it's hard to read the light blue, but is it a time is like this in school, like squared roughly, the growth rate, something like that?
Well, there are these in engineering in the classes. We often show these multi-scale modeling diagrams where we show length versus time, and I'm not sure if it's exactly the square root.
That's
or,
like the diffusion.
I mean, yeah, exactly, diffusion. It's
this was right. Couldn't do it fast enough in my head. I couldn't read some of
this is purely second to second, but this is also something from my experience. This is very, very rough. This is not meant to be an accurate number. This just usually when you're smaller, you're faster. When you're bigger, it's slower. That's the general trend. Okay, so we are focusing for the purpose of this talk on tetrahedra, and a lot of the things that I will show you here. So the first 7 slides are sort of repetition. That's pretty old. So that's from 2009. Actually, the first packing conference in Dublin, 2012, I presented some of the same slides, but I want to bring this up to sort of get us to speed where we're at. And the theories itself mostly are there. So we have a tetrahedron, and a tetrahedron is interesting because you can, yeah, this just doesn't work, because we can get interesting local packing. Like, I mean, this is pretty well known, but we glued them together with some putty. And these are dies that you can use for playing board games. So you can make a pentagonal bipyramid, you can make an icosahedron, you can add more layers, you can make a tetrahelix. And there's the interesting thing here, they're all sort of it's not possible to pack them periodically easily. Because if you have something that has icosahedral symmetry, yeah, it just doesn't work so well with periodicity. So that's why this is an interesting shape. And we ran simulations. Again, this is a movie from 2009. So we put a lot of these tetrahedra in the box, in this case, 2048 tetrahedra. And then essentially you imagine you have this box of tetrahedra and you shake it like crazy. That's what the computer does. And you just wait long enough. And then
You missed it. It spontaneously shook it.
There was static on the screen.
Wow.
All right.
Right.
I'm shaking it now. Okay, so shaking it really. And yeah, and then if you have the magic is if you have the right density, this will spontaneously order, and the right density is about 50%. So this is I think 51 or 52%, I remember. And you can, if you carefully look at it, you see that there's heterogeneity. Like here it moves less, and here it moves a little bit more. And here it's actually ordering. And when it's ordered, the fusion changes and the rotation. So you can see that something is happening, but it's a bit subtle. So what we have to do is we have to put in a coordinate system, and then we cut out some axes, and we can actually see that it forms layers and form these columns. And then these columns, they form, this is a layer, so this is perpendicular, essentially cutting out here such a layer. And I need that later, the structure, because we will see that in the experiment. So you have here these rings. So this is one of these columns, and actually, if you do a diffraction, this is a quasicrystal. So that's something that was super exciting back then, that you can get such a simple shape like a tetrahedron, just a hard shape, and it forms a super complicated structure with this high symmetry. So we were super excited back then to get that, but let's look a little bit more at the structure. So the structure, you have the tetrahedron, and the tetrahedron form these pentagonal bipyramids. So 5 tetrahedra form this green ring, and they can also form this red ring, which is 12 tetrahedra. And the green and the red sort of alternate, like you see it here, like red, green. So the green fits very well into the red ring. And then these columns, they have faces which are a little bit tilted. They can come together face to face, like here into a triangle or in a square. And the gaps can also be filled quite nicely by additional tetrahedra. Here you put 1, here there are actually 4 per layers. You only see 2 at the top, and there are 2 rotated by 90 degrees. So the hierarchy, tetrahedra, they form rings, the rings form these blocks, these columns, and then you can form square and triangle tiles. And then if you have a square and triangle tile, you can tile this. I mean, this is periodic in this direction, but in the other direction, you make a square triangle tiling. So you see the rings are slightly tilted. This will be important to optimize density. And this doesn't work. The adjacent blocks, they are face to face. I mentioned that. And that will be super important at the end. We already in 2009, we observed that these objects are not perfectly flat. So that will become important. And they have some curvature to it. And this one is like, has like positive Gaussian curvature, the triangle. It can be either sort of convex or concave, so both directions. And the square is like a saddle. So yeah, it has negative curvature. And now you imagine if you want to make, actually you can, when I go back, here you can see that a little bit. This is wavy. Yeah, so this is this curvature thing I mentioned. So we'll see that later in experiment. And now if you want to make a tiling, you have to combine squares and triangles just to get 0 curvature and average. That was our rational argument in 2009, why this actually formed and why it's not just squares and not just triangles. This, by the way, is also important in experimental systems. So these square triangle tilings are found in experiments. They are found in alloys. They are also found, we heard yesterday that in block copolymers, they're also the sigma phase, is essentially square triangle tiling. There is also a reason why they don't just form squares and triangles, and often curvature aspects play a role there as well, very similar to here. So another thing we also did, this is a year later, we looked at densest packing. So here it's a mathematical optimization problem, just saying tetrahedra, how dense can you get them? And you start with just, you do it in small boxes, 1 tetrahedra, and you make it periodic, 2, and so on. So these are all numerical results. So the densest packing of single tetrahedra, this is known since, I think, since decades. It's 0.36, so 36%. Then if you take 2, there's a jump to 72. And then you sort of goes to essentially 2/3. And for 4, this one is the densest packing that is currently known for tetrahedra. And there's actually a stick that's helpful. So here's the densest packing. And then of course it repeats when you have 8. You just has to be the same and so on. And we essentially can here see success rate. We do simulate annealing to get these packings, and that works quite well. And interestingly, the densest packing is quite different from the quasicrystal, from this self-assembly result. And we were also aware of that. And that's the last slide from the old work. We made this phase diagram, which sort of was our understanding in 2010. We have a fluid of tetrahedra. Then there is a spontaneous first order phase transition to the quasicrystal. And then there's coexistence. So it's like a first order. When you have first order phase transition, there's always coexistence because there's a density jump. And here, it's the same for spheres. For spheres, you have a fluid, and then you have FCC here. For fluid, the jump is between 49 and 54%, and here it's between 47, and we don't know exactly 51 or 52% here. Then you have the quasicrystal. There's also an approximant. So I don't have time to really talk about that part, but then there is eventually at high density the diamond packing, and in simulation we can never get there because the phase transition is just at 84%. So everything is jammed and there's no more dynamics.
Okay.
Yeah.
So my memory is that the so-called, well, the proven result by I guess it's Colloids and
Yeah.
Gravel and
Yeah.
Vidal circuit is essentially close to 1, right? It's 99% or something. The proven upper bound, I guess there's not, it's just an epsilon less than 1, I think. But
Yeah,
you say it's about 85 is what you get for the dimer.
yeah. I mean, there's proving anything here mathematically. For me, it's totally impossible, but also for real mathematicians, it's nearly impossible. So I think the best that has been proven, it's not 1, so that a tetrahedron cannot pack space, and I think it's like 1 minus 10 to the minus 27 or something like that.
The point, there's a lot of room though for possible improvement in the dimer, but maybe not.
But we did, like, I would say numerically, we did, there was a lot of effort there to really get this better. So maybe there's something hidden. I cannot exclude that. But if then it's only there's only a tiny improvement possible, not much.
Can I ask a nuts and bolts?
Yeah.
With these, did you enforce cubic symmetry way back when?
No.
Okay.
There's actually, you mean this result? This we allowed the box to shear and to change shape, and so this is really the densest packing given this number of particles.
The quote unquote floppy box.
Yeah, we didn't. There's a paper on the floppy box method. In principle, we did the same thing, but we didn't. We were not aware of their paper at that time. We just did it in our way. Yeah. Okay. So this is all old. So, and then our question already back then is, can we do any experimental realization? And we talked to groups with like 7 years. They said, no, we cannot make tetrahedra because it's very hard. The sharp edges are a problem. They're a problem in the sense that when you grow a crystal, and when you get a polyhedron, this is usually a wolf shape. So that means it's a thermodynamically equilibrium state, but it's pretty hard to get sharp edges just because thermodynamics tries to round things. Vertices, it's even harder. Particles also are not pretty hard. So I told you about the ligands. So you have to put the molecules on surface that rounds it and that makes them maybe attractive or just not really hard. And also it's hard to get monodisperse enough. Now in 2021, first time they said, yeah, maybe we can do that. At least we have an idea where we have to go. We need to be, we cannot go too small because then it gets more rounded. We cannot be too large because then we don't have enough thermodynamics. So these things have to be in motion. They have to try a lot of possible orientations. So time has to, if you make things smaller, they're faster. So you have to make them small enough so that you access long enough time scale. So this is the range where you can work at. We can do a ligand exchange. So that means you grow the particles first, and then you remove the ligands and put other ligands on place. The ligands are also, so that way you can sort of make them more hard. And also we can purify them, so we can put them in a centrifuge, or we have other methods to sort of make them more monodisperse. And actually, gold might do it. You can grow a lot of different shapes of gold. It's quite amazing, depending on how you synthesize. You can make rhombic dodecahedra, octahedra. You can make platelets. You can make icosahedra also with them. It's quite amazing, and it's still not fully understood from the experimental side. It's also one other research project we have right now is to understand how we can grow different types of crystals. So an experiment is typically by trial and error. So they put all kind of chemicals in the synthesis process, and then they get certain shapes. And they know exactly, if I follow this recipe, then I get this shape, but it's not fully understood still today what is happening there. So yeah, in 2022, one of my collaborators, he took me apart. Actually, several groups are working on this right now. So I'm aware also of other groups who have very similar results. So Xin-Ching Ye was the collaborator who we talked about in summer 22. He told me, I think we have some important progress recently on this problem. And this is what he showed me back then. So this is the particles you can make. You see the edge length is 50 nanometer. I hope it comes quick. There it is. So here you see it's still a little bit rounded. So here we call this the truncation parameter. This will become later important. So it's just 1 minus L2 minus L1. So yeah, they're good enough for our purpose, as we will see. So, and then you put some chemistry on the surface. So this is sort of a sulfur, and that's very often used in gold because it binds pretty well with the gold surface. And then there's essentially, you can think of it like a long alkane, like hydrocarbon chain, and there's some functionalization at the end. They're actually slightly charged so that they don't stick. And luckily, I don't have to worry about that because as a theoretician, we just get the particles and they just work. And then you dry them. So you put these particles in solution, you dry, and what you get here, and we'll look at that in a second. So essentially, they form a thin layer on a substrate. And one of the key things to do is you have to make the substrate hydrophobic, and I will explain a bit more why. And then when you make this, they form these droplets. And let's actually, if you zoom out, this is how the sample looks like. So this is sort of what you see under the electron microscope. It looks a little bit like your windshield when you drive in the rain and you just went to the car wash before and there's wax on the surface. So it forms a very tiny droplets, and that's essentially what this is. So droplets of these material on the surface. And then you zoom in, and this is sort of one of the droplets. And you get here now, you see here all the tetrahedra. They form these rings we mentioned before. And let me zoom in a bit more. Actually, here is first the diffraction image. Interestingly, the outer is six-fold, but already here you see that it's 12-fold. I will get back to the six-fold in a second. And then you can look from the side, and here you see the tetrahedra. They form these layers that I mentioned. So it works pretty nicely. You form here, here it is a zoom in. You see here the layers. And so this perpendicular direction. And now you can do tomography. So we look from different directions, and then we can extract features. This is one of the columns. There's really experimental data that we cut out. And sort of you can look along the column and you can go through here. And this is sort of this column. And now you can cut. So my colleagues, they used what's called a focused ion beam FIP tomography. That means we first try to see through the sample, but gold is pretty electron dense, so you cannot really see through it easily. So FIP will prove to be the best option. So that means you start with the sample and it's a destructive technique. You just layer by layer cut it away. And it's just like you see here. And then you image the different layers. And then, for example, you get layers like this. So this is the height here. You can do this quite precise, up to a few nanometer precision. And then you sort of here you see here the tetrahedra cut. And this is sort of from the simulation. So this is from our simulation result, we also simulated this cutting. And then we get that, and you see a pretty good agreement. And even small features like here, this is here the rings, and here's the center of the ring. You sort of see here exactly the same thing. So in the paper, this is shown, and you can really like here this tiny gap. It's like just the tetrahedra cut along the edge, and you see part of the edge. It essentially works super well. And then we can do here. This is a movie in a second, so I will run it. So we will essentially go in the set direction through the structure. This is the experiment, this is the simulation. And here you see the rings I mentioned. And what you will see if you look at the rings, here's another ring, it will alternate between the yellow, this five-fold pentagonal bipyramid, and the purple, which is the 12-member ring. And I will just run this now, and you'll sort of see how we go through here, and it works pretty nicely. And you sort of can go here around the columns. We see here the triangles and the squares, so we see the tiling that I mentioned at the beginning.
Is there any long range order, or is it mainly the short range rings which are not really correlated over larger distances?
It is long range order. It's a quasicrystal, really.
Okay.
I'm not sure. Yeah, actually, I don't have in the paper. There are the small angle X-ray data. I just didn't have time here. But you can put it to the synchrotron. You can put it under, essentially make diffraction like you would do in a real crystal. But now you have to, because the structure is large, that means you have to go for smaller angles. It's inverse. And then the small angle you see the small angle peaks.
Because we have polycrystals, big or small.
You essentially, if you go back, this thing is a single crystal.
Oh,
the majority. This is a single crystal.
is this a coating of the surface of the droplet that you have?
No, it's bulk.
It's bulk.
It's the whole thing is a single crystal.
Okay.
You use the water to hold it together.
This is not flat, but I will get back to this. This is dried. This is dried and it's slightly curved, and the curvature will be important. That's why I spent some time at the
I
beginning
was
to.
gonna ask.
Just wait, because that's sort of the end of the talk.
Sorry, Michael.
Yeah. I'm almost done. The curvature is actually the last thing, but maybe there's also another aspect, but I will go through this real quick. So what you can do is you can change the degree of truncation, and you get these twin shapes. But what you already see here is that the particles, they form something periodic, and that's what you get when you change the truncation. You get these really beautiful superstructures, and I'm pretty amazed by how monodisperse they can make that. And this group can do that, but there are a lot of groups working on nanoparticles which can make very complex, very regular shapes. So here's a zoom in, and you just see, if I would do this by hand, I probably couldn't do it better. Like you can see here the layers. Here's another one, zoom in. You can see here the tetrahedra, and here's a grain boundary. So here's one crystal, here's another one. It's like FCC, HCP a little bit. Actually, in this case, because it's with tetrahedra, it's diamond and another version of diamond, like hexagonal and cubic diamond. And this comes back to these densest packings I mentioned at the beginning. You can construct these. There's a cubic diamond variant. There's a hexagonal diamond variant, and all of these are found also in the experiment if you look long enough. And which one you get depends on the degree of truncation and also the experimental condition. Actually, the way you get these, like in the simulation, you get them at high density, but you have to do heterogeneous nucleation. So the quasicrystal forms with homogeneous nucleation, but if you make the substrate not hydrophobic, hydrophobic but hydrophilic, then you see that here, then the salt solution wets the surface, and then you get the tetrahedra pushed down, and you get growth from the bottom. And you can even improve this by adding nucleations, and then you get even more heterogeneous nucleation, and you get other phases. But let's get back to the truncation, and that's the end of the talk. Two more slides. So this one is really curved. We can put a tiling on top. This again shows it's a single crystal. But what you already see here is that there's an asymmetry. There are these blue triangles and the red triangles. So something is not quite as regular as in the simulation. So here we analyze the tiling, triangles and squares, and we can then look at local environments. These are called vertex configurations or vertex figures. We can use this notation that's common in tilings, which just says how many triangles and squares you have around one vertex. And so yeah, they are curved. I mentioned that. And now it becomes important that these triangles and squares are curved. And now you can, here's sort of how this would look like, this wavy surface. Now imagine you have a curved surface. What would you? If you have a curved surface, and you have now triangles and squares available, well, the idea is maybe you get a bit more triangles than squares. So let's do that. So let's start with a large one, and then we go to a smaller one because we have droplets of different sizes. Here, look at the ratio of the concave to convex triangles, and then you get more triangles. And then even more triangles, and eventually, if you have a small droplet, you only have triangles left because it's curved. So that shows us that the curvature can change the tiling itself, and this actually shows it's a very well equilibrated system. So it can access not only the quasicrystal, also different tiling geometries, and essentially that's the end. Thank you very much.
So yeah, Tommaso.
Just very briefly. So the quasicrystal one is essentially two-dimensional because you have these rods, is it?
Yeah, it's periodic in the third dimension. Yeah.
That's it. Yeah.
One clarifying, one
Yeah.
leading question. the truncation parameter you were talking about was a ratio of the two different side lengths essentially. So not like our typical vertex truncation parameter, but a kind of particle misaligned.
Yeah, this is something that the experimentalists use that parameter like this, but it's you can convert it into the other parameter.
Well, not necessarily. But my question was more about like the diamond structure that you assembled, because that's quite difficult to make.
Yeah.
In colloids,
Yeah.
is it similar to the truncation effects that we saw with like Pablo and my work, or is it? Okay.
It's the same idea, yeah.
Okay, same idea. So you think if it's continued to be rounded and rounded and rounded, we would still see that same phase transition?
Yeah. We have seen in simulation that essentially what happens when you have truncation, then they can flip when they get together because the vertices are in the way of them flipping. And then
Well, we saw uniaxial phase transition in the truncation family. That's why I'm curious if it's divergent, if it's within that truncation parameter. We can talk more about that.
Maybe one quick clarification. So the experimental PMVW is an abiotic, 2D abiotic structure, right?
Yeah.
So how did you align the simulation experiment?
Well, we had the tomography, and when you have tomography, you have a three-dimensional structure. So it's not just you can just rotate it in whatever way you want.
But you have to sort of somehow simulate the same local structure and build it out to get the identical origin.
Oh, you have to find similar environments. Is that what you mean? Yeah. Well, we looked in the simulation. Where do we have this?
Do I see these? Okay, that's right. And then the second thing at the end, your structure is sort of like has a z-axis.
Yeah.
Right. It's like, and so the droplets are kind of probably not going to have the pancakey or whatever.
Here it is pretty flat actually, but that's also because
I guess you with the Gaussian curvature is interesting because you sort of would say, or somebody would say that the integrated Gaussian curvature is for the whole droplet is a number, right? And that's going to tell you something is compared between them, but this is a little bit different because it's only for the 0, 1 line or whatever you would call that direction.
Yeah, it's an interesting question. Usually the top hole direction actually points in this direction. We don't know exactly why that is, but maybe because it tries. I mean, I would imagine these droplets they're actually at early stages they are sort of floating on the substrate. They try not to touch the substrate as little as possible, so they can probably rotate around, and because of the quasicrystal, it probably wants some ellipsoidal crystal shape, and then it just rolls with a flat face to lie on the substrate, and that rotates sort of the 12-order axis towards the observer. That's how my guess. We don't know that, but that's at least possible.
One last quick one. Maybe I didn't get really, is the spherical shape that we see here something that's related to the drying process, or is it something built into the structure that the interaction, the way things assemble, that wants the whole external shape to be spherical?
It's a drying process, I think. The majority, at least. There is a bit. I think it seems to grow more easily in plane than in the outer plane. So we know also from crystal growth that crystals can grow very anisotropically. There's a little bit of that, but the majority here is just because of the hydrophobicity of the substrate. You start with a film, and then the film breaks into droplets because that minimizes the surface energy, and then the droplets just dry out.
So it's the surface tension of the droplet which is more important than the energies involved in the layering that you have that would favor growth in a specific direction that would flatten maybe the droplet.
Yeah, the energy in the droplet itself, the surface energy is pretty high and much higher than the entropic effects that actually assemble the particles.
What's the density here? How large is this part?
This is 10, 20 microns. the whole thing. The nanoparticles are 20. So there are typically 1 million tetrahedra in one of these.
Thank you very much. Sorry, one quick one.
Quick question. Just coming back to the last question, if it's a driving process, if the capillary forces between particles, does that play a role, or can we just think of this as the whole object is compressing slowly? I mean,
Yeah, we were actually asked that by a referee as well. We think that this. I don't think you were the referee. I think that this ordering happens when the tetrahedra are still completely in the liquid, so that at that time there are no capillary forces. Essentially, you imagine like it's really a droplet of water with the tetrahedra inside, and then eventually the droplet evaporates, but then everything's already arrested. So once the capillary forces appear, the particles cannot move anyway because they are jammed together. Sort of, this happens at a very late stage.
thinking, cool.
Let's thank Michael.